Welcome everyone. I introduce myself. My name is Chris Bayliss. I'm the Climate Change and Decarbonisation Director with ASI. Delighted to be your host today for a webinar specifically focused on ASI's ASI method, the Greenhouse Gas Pathways method. We initiated this webinar in response to a request that came in from my co-panelist today, Mr. Gangaa Sharma, who is Managing Director and CEO of CETIZION Verifica. He's an ASI accredited auditor. He has lots of experience doing ASI Performance Standard and chain of custody audits. And he came to us and said, look, entities are struggling with how to both gather greenhouse gas data to understand what greenhouse gas data to gather and to use ASI's tools. And so today's webinar is really a focus on that data gathering process, depending on where you are in the value chain, and the use of ASI's tool, our calculation tools. I'd like to quickly take us through today's agenda. Welcome is almost over, don't worry. And then we're going to go into a couple of case studies for greenhouse gas data collection and disclosure and use in the tool, and they're going to be led by Gangaa, prepared by his team. 2 case studies, possibly 3 case studies for different entities or different parts of the value chain. So you'll see some examples from upstream, primary production, some from right downstream, material conversion, foil rolling, and maybe some in midstream as well, where it gets a bit complicated with scrap inputs as well as primary inputs. And then I'm going to be showing you how that data is used within the tool. So we're actually going to work in Excel and to show you which data points, which fields to populate with what data, and then explore some of the outputs of the tool and what they can be used for, both ASI conformance, performance standard conformance, objective evidence purposes, but also other purposes as well, regulatory or strategic or communications. And then we're going to go into a Q&A, and I hope we have about 15 minutes for that. So with that, if I'd like to turn over to Gangaa to take us through some of the case studies, or these case studies that he and his team have prepared. So Gangaa, if you're available, I know that you've been traveling. Welcome, hi. Please take it away.
Okay. So thank you, Chris, for setting the contest, and welcome all the participants. It was a request by many of you, and we also feel during our audit interaction that we need to talk about it. It's very important requirement, and with the CBAM on the card, it's getting more attention. So thank you, Chris. Without losing time, I'll get into. So the first thing before starting the tool, we need to understand the data. What's the input data? So in this next few slides, we try to capture a few examples and to inform you how to set the data scope and boundary and how the data flow. So it's just an example. In your organization, it might be slightly different. The way you capture, few companies use automated tool, few does it manually, Excel based, so it's vary. But the point is that the nature of the data doesn't change. So let us take you to an example for the smelter, which is I would say choke point is the highest priority in terms of the energy. So if you see the smelter process, the alumina is an input which is coming to the smelter. Then there is a carbon plant on the side of it where we make the anode, which is consumed, and electrolysis process happening between anode and cathode, and the molten metal, the liquid metal, come out of it. And further, it in the electrolysis process, there are some process emissions. If you see anode which have a carbonated, it's burnt. I'm trying to explain you in a very simple language. And a lot of process emissions coming out of it, which have a GHG impact. So That's quite different from the rest of the activity where hardly any process emission happening in the aluminium value chain. And then you might have seen the people from the smelter. There is a gas recovery system in which aluminium silica coming back for the process efficiency. And finally, the molten metal, which is tapped from the port, is further taken to the cast house, and it's created a bath. The slag we called the skimming of the dross is taken away, make the composition as per the aluminium grade, and finally transform into the different product. Uh, Typically, the ingot, SOW, billet. Generally, these are the major wire rod. So next, so what? So this is mainly the scope and boundary. So if you see in a smelter, there is a direct emissions which is coming from during electrolysis process. There is emission from CF2 and C2F6 anode effect. There is a fossil fuel generally, depending on the where we are in the world, we use different fuel based on, say, it could be coal, it could be LDO, which is a form of a diesel, furnace oil, HFO, etc. So these are all combustion happening within the boundary of the smelter and come under direct emissions. On an indirect emission side, there is a electricity, either it's purchased or company might have their own captive power plant. And then there is a scope 3. And from ASI point of view, under scope 3, we are not concerned about all the 15 category. We are focusing on some major contributing category, which is purchase of the goods, which is the alumina per se, category 3 and category 4. Next, please. So we need to know the data and the emissions. This is an example if you need to calculate the process emissions, we need to understand the a basic thing like what is the ash content in the back anode, what is the anode effect, which is a very important process parameter also, and I would say show the health of the process. And based on that, by having a formula, the emission factor behind, based on the activity data, we calculate the emissions. If you go on the right hand side, so this is, if you see on the left hand side, 412 is a typical example for a thermal power plant as a captive power source, a typical smelter in India. We try to uh, put the data which is quite close to the reality for a smelter of around 300 kT capacity based on the thermal power plant and fueled by the coal. It's a typical combinations what we can see in Indian context. And based on that, we try to list out all the activity, like how much is the pitch consumptions per anode, how much is the packing coke, how much is the back anode productions. So if the people who know the smelter know about it, but this is a systematic way to calculate your process emissions. So go on the right hand side, then based on this, the total process emission is coming around 562,202 tons CO2 equivalent. And this is the base year for 2025. Next, please. If you see, then coming to the other direct emissions like burning of the coal, burning of the diesel or natural gas, or it could be other source of fuel. And based on the formula, like we convert into the gigajoule, then we have the emission factor. We came to know about the total emissions of CO2 equivalent. On the right hand side, the indirect emissions is basically the purchased electricity. Generally, depending on the power mix and the locations you are, the agreement you have with the utility, there could be different source. So we take a typical example in an Indian scenario that it's a captive power plant, and we have grid power import. Uh, we have a grid power conventional import purchase electricity, and then there's a total direct emission. So generally company they have buyback system. They produce the power, give to the grid, and then take it back. So depending on the consumption, either you burn the coal for your captive power plant, then your direct emission will go up, scope 2 would be reduced, or if scope 2 is high, then the equivalent portion scope 1 would be equally compensated. So we have to calculate these. Process emission is the key part in the smelter. We have to be very careful about it. Rest is quite straightforward in the direct, indirect, and the is category 1, which is the alumina. Next, please. This is a typical example how the purchase goods and services, like we buy alumina, we buy fluoride, we pet coke, and category 3 is fuel and energy related. We called FERA based on the factor. And then we have the upstream transport, which is quite significant in case of if I'm buying alumina from uh, refinery in Australia or from Brazil, and then in turn they buy the bauxite. So it's a typical and complex upstream value chain, and we have to know about it. And sometimes it's a significant part of the emissions mix. So that's how a smelter has to calculate its emissions, which is going to be the input. And Chris is going to tell us that based on these calculations, how the tool is going to work. So this is one example of a typical smelter. Many time what happens, smelter does not have the carbon plant. And we have seen in few audits. So they take the anode from their subsidiary. But when you calculate mine to metal emissions, then you have to add your anode related emissions also in your calculation. It doesn't mean if it is not happening within your boundary, you are going to, otherwise it will not be a apple to apple comparison. So that's how, as I said before, companies based on their internal setup, there might be different forms looks like, but as far as the expected outcome is concerned, you have to make sure that you are not missing any significant emissions attributed to your smelter activity, which is going to be used as an input into the ASI tool, which Chris is going to explain. So it's a typical example of a smelter. Now we can talk about little bit how the downstream. Okay, go back. Yeah. So based on the previous slide, if you see, we have collected all the informations like scope 1 and 2, scope 3. So these are the numbers which are really going to matter and going to be used in the ASI Excel tool. Next, please. Now let's discuss about a downstream company making foil. So foil generally, the people who knows it, there is a process. So we buy the foil stock from the cast house or the rolling flat roll product companies. Then it's unwinded or rewinding happening. Then there is a rolling mill, depending on the thickness. And if you are making ultra gauge thickness, you might need intermediary rolling mill, then finish rolling mill. And then there's a term they called use doubling, and then final thinning, and finally separations. And based on the aluminium grade, either you need hard, toughness, based on the mechanical properties, the heat treatment has been carried out. And then quality assurance is a typical flow of foil production. So as a foil manufacturers, what does it mean for me as far as the GHG emissions is concerned? So let's try to understand what are the various source of emission in a typical foil industry. It's going to be direct and indirect. There is no process emission in foil industry. Typically indirect, you use diesel for the forklift or for burning. It could be used for the furnace also, or it could be used for other applications like diesel generator, for example. Then you have electricity. Either you have renewable energy or you have own power generations. For example, we have seen some of our clients in Africa. They generate their own electricity even in the downstream side. So depending on where you are, the electricity related emission has to be done. And then there is scope 3 category 1. So as we go to the downstream, it is bit relaxed, and main focus is on the category 1, which is the purchase of aluminium as a foil stock, or if it is can company, can stock, because that is carrying the highest embedded emissions, and which is really matter for us as a aluminium company. Next please. If we see, for a typical, we try to see how the number looks like for a typical foil company. Again, we consider based out of India to have a continuity of, we keep the smelter example of Indian contest with a thermal and typical. So for this particular case, general the diesel is only used for forklift or some other applications, and it's around 48 ton CO2. So generally you will find the scope 1 is not very high in a foil industry. When we say energy, because of the rolling mill is a quite a energy intensive equipment, is running 24 by 7. Then the furnaces, the annealing furnaces also consume a lot of electricity, or if it is gas, it would go to scope 1, and if it is electric fire, it come to the scope 2. And then rolling mill and annealing mill, that's one of the quite significant in a foil mill, is around 10,096. These are the number based on a company, a foil mill making around 1,000 ton per month, or around 12,000 ton per annum, the foil production. Scope 3, as I said, it's a highest contributor in a foil company, and coming from the uh, purchase of the foil stock or can stock if it is can company. And if you see other related requirement of ASI, when we talk about responsible sourcing, we asking you to work with your supplier to buy, because you as a purchaser can influence those decisions to ask your supplier, and in turn it's the pressure goes up to the smelter to provide you the low carbon, I would say, product towards the downstream. So this is a typical combination, and a foil company, or it's a generally the downstream company, if you'll found scope 3 is always high, followed by scope 2, and followed by scope 1. It's a typical uh, mix, I would say, looks like for a typical foil industry. Next please. This is a further detailing. If you see, like in this case, the diesel we use for the diesel generator, and based on the calculations, we came out in terms of how much uh, liter per hour of working. Every company have its own log, uh, and then with the emission factor, you can reach out to the emissions equivalent CO2. Likewise for electricity, if you know the, like in Indian contest, if you are taking the electricity from the grid, which is a mix of thermal and renewable, every year the regulatory authorities give a emission factor for the grid, unless you buy a guaranteed electricity from other third party, and that emission factor has to be taken. So when you have two options, it's a very classical case in India. So we have some international factor, uh, IEA and others. But once you have more reliable power factor for your own national grid, that is always suggested to pick it up. And this is many companies doesn't know about it. So our request is to keep yourself updated, because it have a huge impact. Even 5-10% variation in picking up the wrong emission factor can change your emission profile as a final product. And then scope 3 is always quite high as we go to the downstream, and you might have seen a lot of requests coming from the downstream company and creating pressure on the smelter, and further goes up to the bauxite and refinery about traceability and the GHG profile. So next please. So that's how a typical foil company looks like, uh, and now we are going to use this data. If you see how the 48.18 comes, uh, this is, if you see, one of the requirement 5.4 of the standard GHG management system. When we say management system, we expect you to create a system inside which have a clear metering, measurement of the activity, responsibility, because if any ambiguity happening in these, at a base level, at a data at source, quite obvious that whatever tool we use, it's not going to be reliable. So please work with your internal system and make sure that you have a very correct activity data is captured wherever it's happening, be it weight or be it metering, or so it should be. And this is a gray area, I would say. Generally we talk very big thing, but we go down to the shop floor and we found, hey guys, the gentleman, he or she or otherwise who is responsible is not really understanding the context and the accuracy requirement of this data, or the meter is not working, for example. So please look into this. And because the numbers is the output of the process, and we always say, hey, work on your process, and otherwise tool will not give you the result what it can give you in more accurate fashion. Next please. Likewise, for scope 2 is a further classifications, how much grid electricity we are using, how much captive electricity we are using. No, there is a trend. I would say that many downstream company have rooftop solar or they have a captive wind farm. So please consider that. Only challenge that generally they don't have the round the clock power assurance, because generally company running 24/7. So you'll find larger portion is still renewable, but it's still 5-10% they're still buying from the grid electricity as a power backup, because it's very hard to have such a large storage device in your company. So that's how a foil company looks like. Scope 3 is always high, followed by scope 2, followed by scope 1, and that's a typical GHG emission profile of a downstream company uh, looks like. If we lucky to have a low carbon aluminium input, that this balance might change, but more or less this is the situation as on today. I think Rian, we done with this. So this is more about how to do in detail the calculation for scope 1, 2, and 3, and which is going to be further used by Chris, and explain you how to use it to derive your GHG reduction pathway and target. Make best use of it. And Chris, I think over to you to teach us, I would say, how to use these numbers to get more reliable and credible information.
Thank you, Ganga. We actually had a question come in over the weekend about the midstream, and I've put together just a quick case study on that, just to kind of explain some of the important role of scrap in Scope 3, and I'll use that in the Excel in a moment. The thing about the midstream is that you have your direct emissions, like for the foil rollers, and by midstream I mean those that are creating extrusions, flat roll products, semi-fabricated products, often with an integrated cast house. And there you have direct emissions associated with both the cast house, scope 1 generally because they're thermal processes, and with the rolling mill or with your extrusion press, predominantly scope 2, using electricity for those processes. So the gathering of data is similar as for the foil rolling, but will be more dominated by scope 1. But the scope 3 emissions come through in this procurement of aluminium, scope 3 category 1, as Ganga mentioned for foil. But here you'll be using cold metal inputs to your cast house, and that may be primary, it may be some kind of mixed remelt ingot, and it can also be scrap. So importantly, the treatment of scrap here is a thing to consider in the midstream, and how you allocate emissions to that. Often people use a cut-off approach, allocating 0 emissions to that scrap input, and so that has to be mass weighted with the primary input into the cast house. You can see some examples on the screen now, and I'll talk through it in a moment. Importantly, you have to include a yield here as well, because the scrap is not 100% remelted into aluminium. So even though you're looking at the procurement emissions, you have to factor in a yield, 90 to 95% usually, depending on whether it's pre or post consumer, and then mass balance that with primary. But let's get onto that in a moment. Our tool is based on a sectoral data set developed by the International Aluminium Institute along with Mission Possible Partnership. In fact, the scoping that we use is the same as the IAI's carbon footprint guidance, International Aluminium Institute. So do take a look at their material. It's also linked from our guidance. So that's the place to go to understand full scope, especially for primary. Using that IAI data, which describes a sector-wide emissions reduction slope out to 2030. You can see the red line here. Essentially, we developed an entity-level approach that maps given baselines, so this is for primary aluminium, and a range of baselines from around 4 tons of CO2 per ton of aluminium all the way up to 25 tons per ton of aluminium. The variability really being driven by power generation, whether it's thermal power at the upper end or hydropower or nuclear or other renewables at the lower end. But describing from that given baseline performance, a trajectory towards 2050 and convergence on a sectoral emissions intensity number. This is called a sectoral decarbonisation approach. Those of you familiar with Science Based Targets Initiative will know about those, what we call SDAs, sector decarbonisation approaches. But what you can see here is that there is a variability in slope depending on your starting point, but essentially all describing a similar slope towards 2050 convergence. And that's what our tool does. It essentially uses your input data in the baseline year to map a given slope out to mid-century. And that can help you set targets and provide conformance to ASI under the performance standard. We had a question coming in, which asked about data protection. And I'd like to say at the beginning that the tool I'm about to describe is freely available on the ASI website for both ASI members and non-members, and no data comes to us. Right, so it's an Excel-based tool that you download and operate from your own computer using your own data, and you never actually share any data with ASI. So really the question of how we treat that data is irrelevant. We don't get access to that data. What that data is used for is to talk to your auditor during audit to demonstrate that you have targets that are aligned with the tool's slope. So that's a discussion between you, the entity, and the auditor. There were some questions as well have come in around CBAM and the role of the slope development in CBAM. CBAM has some specific data requirements, and if you are conducting verification of your data for CBAM, you have some of the bits of information that will be needed for the ASI method, but actually CBAM only asks for a subset or only charges according to a subset of your emissions. So the data you need for ASI, if you're doing CBAM, you have some of the data. If you're doing work for ASI and you're completing our inventory, as Gangaa mentioned earlier, you have all the data you need for CBAM, but you might need to make it a bit more granular for CBAM purposes. So this is a really important point across all greenhouse gas accounting, is that there is no singular way of presenting emissions data. Different data sets, different scopes are used for different purposes, and CBAM has a different scope from the ASI method. ASI method is cradle to gate, it's a life cycle approach. It encompasses both process emissions or those within your corporate boundary, but also your scope 3s as well. So it is a much broader range of data, but it doesn't have the granularity that CBAM requires. What's really important for meeting CBAM requirements and our requirements is that you need verification of the data, and you need a good way of managing the data as well to answer the different questions that are being asked of you by regulators or by customers or by ASI. So I'll echo Gangaa's point that you need good management of that data, with output of that data being different depending on the purposes you're going to use it for. So now let's look at the purpose of ASI, and the use of our tool. I will explore each of the different case studies that Gangaa mentioned, but before I do that, let's have a quick look at what the tool looks like in general, what you would see when you are let me just when you are approaching the tool. And what we have is it's Excel based, so it should run on most of your machines. If you're using an older version of Microsoft, we have some legacy versions available, so do get in touch. There's lots of tabs along the bottom, and what I'll show you today is a truncated version, so kind of smaller tabs versions, but some important ones to note. Under the user guide, you're going to see these different worksheet color codings. And you'll note that there's only some where you have to enter data. And today I'll only talk about a few fields that you enter data into, because the majority of the tool is actually output. It's giving you information based on the data that you enter. Some of that data is optional, and there's lots of auto calculations going on in the background. Essentially, there are two tabs of interest if you're for entering data. Or three actually. The first of those is for everyone, no matter where you sit on the value chain, and it's choice of baseline year. It can be as early as 2016 or it can be as late as 2024. And once you've chosen your baseline year, that flows through the whole of the document. If you're a smelter doing primary production, you'll be entering data using this primary tab, 100% electrolytic. If you have any scrap in your system, you will use this blue one, the cast house and post cast house. And that's also for the mid and downstream as well. And I'll explore that in a moment. So let's go right in there and start looking at the primary example that Gangaa showed us earlier on. Here we have the primary tab down here, the primary 100% electrolytic. First thing we do is we go in and choose our baseline year. Let's hope this one works this time. So yes, you can choose your baseline year as early as 2016 or as late as the previous year. In Gangaa's example, 2025 was the baseline year. So we would choose 2025. Some have 2018. Often it's pre-COVID. Not many have 2020 because it's a COVID year. So you choose 2025, and that's the only time you need to enter your baseline data. And then we come into the primary piece. So just click on the tab. And in Gangaa's example, it was one smelter. It was a smelter, Indian smelter with its own thermal power production, its own coal-fired power plant. Remember, they were the direct emissions, the scope 1s, but also had a grid connection. So there were some emissions coming in as scope 2 as well. This tool, you can have multiple smelters. So you could have within your entity 3 or 4 smelters, and you only need to describe one pathway across all of those smelters. And our tool allows you to do that. It essentially mass weights these different elements. So if I had a second smelter that was, let's say, 300,000 tons and its emissions were, I don't know, 16 tons per ton, you can see that the method here actually calculates a mass balanced cradle to gate emissions intensity across those 2 smelters and describes, what I'll show in a minute, the slope across those. So this is a great way actually in this tool of having multiple sites within one entity and then describing one target for all of them. But for simplicity's sake, let's just take the one example that Gangaa showed earlier on. It's a smelter with a 270,000 tons per year production. And remember, the emissions data Gangaa showed earlier on, it was the scope 1 and 2 was 15 tons per ton, and then there were scope 3s coming into the equation too. Well, we have to incorporate those scope 3s into the intensity factor. And the way that we do that is by adding the total scope 1 and 2, 4 million tons, plus the scope 3s, 993,000 tonnes, divided by primary production in the baseline year. And that gives us not a number of 15.1, but actually 18.8. Because it's cradle to gate, it must include those scope 3s, and they're coming in as alumina or purchased anode if you're not producing your own anode. So 18.8 is the number to add, and that is done in one field here under the cradle to gate emissions intensity, 18.8, along with the corresponding production value. Now, that's all you need to do. Those two numbers are all that you need to enter into the tool to describe a given slope. And that slope is shown in this line here. So that is row, let me just see what row that is. That is row 14. That is your, essentially, you can then copy this data. That's your slope that is 1.5 alignment. It describes 1.5 alignment. It's shown down here on this tab, this slope from 18.8 in the baseline year 2025 all the way down to 2050. You can see significant drop post 2030. That echoes the sectoral data. And that's all you need if you're a smelter to describe ASI conformance for the performance standard. You need to have an intermediate target within 5 years of your baseline year, 2030. So your intermediate target would be something like 16.7. You can see it's around here. But the slope, of course, describes everything to mid-century. So there's a short term where you use this slope, but then you may want to describe a longer term as well. The ASI method is also available for you to describe separately your electricity and non-electricity related emissions. And the electricity could be self-generated or it could be purchased, scope 2. So you can see down here, we've done a bit of a calculation drawing those two together to give an electricity intensity of 13. That's to say that of the 18.8 tonnes, 13 tonnes comes from electricity. If you add that into this optional box on column F, you actually have described different slopes for your electricity and your non-electricity. So we know that some entities like that. They like to have this separation in slopes, and so our method can be used for that. It's entirely optional. You can give a total or you can give a split. So that's primary. It's actually relatively easy for the primary. Relatively few data points required. Let's look at this foil example, which was the next one that Gangaa showed. Foil in our system, it takes a semi-fabricated product and it re-rolls that product, or it further converts that product. And so within ASI, that's treated as material conversion. And material converters in the ASI method, they have an interesting position because while they have direct emissions, as Gangaa demonstrated, they're dominated by scope 3 category 1s, their inventory. And within the sectoral boundary, IAI, they're not included. And so within our system, it's very difficult to develop slopes for their direct emissions because they're not in the sectoral budget. We don't entirely know how their slopes might look. And so in our system, knowing that the input material, the scope 3 category 1s dominate, we only ask material converters for ASI conformance to show slopes for their procured material. They don't need to show scope 1 and 2, their direct emissions, only scope 3 category 1. And so that means there's only one data point that needs to be entered by these entities. And for material conversion entities, it's this field here, field E22. It's the average carbon footprint of purchased aluminium in a given year. And you'll remember from Gangaa's example earlier on that that number is 19. Not 19.71 because that includes the direct emissions. It's just 19, which was the purchased embedded footprint. So if you're a foil roller or you're a can manufacturer or you're an OEM doing secondary castings, or let's say giga castings, or you're a secondary cast house yourself, this is the data point you need to enter. It is only one piece of data, the procurement emissions footprint, and you enter it in this field E22. So having entered 19 in here, the output that you get from the system is a slope for your procurement only. It looks similar to the primary, but it's not cradle to gate. It's only on your procurement. But you can see it has a significant drop again post 2030. So if you were this foil roller, and you had a baseline year emissions intensity of 19 tons of your procured aluminium, by 2030, when you would need your intermediate target, you would be looking at something like 15 tons per ton. Quite a significant drop. This is why we've developed the exemption process. That's not for today. I'll talk about that another day, maybe. So if you're a foil roller, it's only your procurement emissions that are required. It's only one data point you need to put in, this 19 here, and it is a description of your procurement emissions only. Let's look at that third example now, which is probably the most complex of the three, which is for an integrated cast house and rolling mill. So in the ASI system, that would be semi-fabrication plus casting. Okay, so again, you use the blue tab, the blue tab at the bottom, which is for cast house and post cast house. You choose your baseline accordingly, and the data you enter, well, there's a number of bits of data here. The first thing you want to do, and you'll note that actually instead of this row E22 as we had before, where we put the 19, you're not using that. You're using the two rows above, which are related to casting and semi-fabrication. Semi-fabrication being your rolling process. Okay, and in this entity, what we have are a number of different things. We have remelt ingot coming into the cast house. We have scrap coming into the cast house, and we have slab externally purchased or purchased from an external coming into the rolling mill, as well as the use of the integrated slab that's come from the cast house. So you've got quite a bit of complexity there. But the first thing to note is that you will have some process emissions. And those process emissions on the cast house, let's say we can see them down here. We have an output of cast house of slab of 250,000 tons. The first thing we do is add in 250,000 tons up here. We have gate-to-gate emissions, that's to say scope 1 and scope 2 in our cast house. You'll remember dominated by fuel combustion. 150,000 tons from fuel combustion and 10,000 tons of CO2 equivalent coming from electricity use in the cast house. So that's 160,000 tons. 160 divided by 250 equals 0.64. So we add 0.64 up here as our intensity. For the next phase, for the rolling mill, it's the scope 2 that dominates because we're using electricity in our rolling mill, and scope 1 really immaterial, so I've made them 0 here. But the output of our rolling mill is higher than the cast house. The reason being we're purchasing in some slab from outside. So the production for the rolling mill is 350,000 tons. 125 divided by 350 equals 0.36, and that's what we add into this table here. So this table at the top is for cast house. This next table is for semi-fabrication. And as before, you could have a number of different sites all entered here, and it would be mass weighted. You must put in the different productions because that is a denominator that is then used for the mass balancing. So these two elements, 0.64 and 0.36, the system pulls those down here into column A. You can see for cast house 0.64, semi-fabrication in 2025 0.36. But then what you need to do is to add in your scope 3s, what comes into the system. And I'm going to start with the semi-fabrication. The semi-fabrication, taking in the slab, it includes both the slab that you have purchased from external, but it also includes the slab that has come through your system. backing out the scope 1s and 2s. The rolling mill is only looking at the slab that you're pulling in externally, because your own cast house is going to be pulling in the scope 3s in the remelt ingot. So it's important that when you're adding data here, the scope 3s you're adding in for the cast house will be remelt ingot and scrap. But for the rolling mill, it will only be the slab you have purchased externally. It's why you can see two different numbers up here, 13.7 for the cast house, that's your remelt ingot, plus the scrap, and 18 for the purchased slab. And all those numbers are indicated below. We're going to share this material afterwards so you can see what that looks like. You enter those data and you must enter the mass of the aluminium input as well. That's also taken from the data below. And what this describes are two different slopes. It's one which is an integrated scope 3 category 1. It takes your cast house scope 3s and your slab scope 3s externally purchased, and it describes a single slope for all of your scope 3s across the whole of the integrated process. So starting from 14.2, something like that, you would then have a 2030 number of something like 11.5. But it also describes scopes 1 and 2 slopes. An integrated one, if you want to use that between cast house and rolling mill, or separate for the cast house and the rolling mill as well. So these slopes for scope 1 and scope 2 are part of your performance standard conformance. You have to demonstrate, if you're midstream, both a purchased scope 3 slope and a scope 1 and 2 direct slope. So there's a bit more complexity in the midstream. You have to separate out your direct emissions and your procurement emissions. And if you have multiple processes, you have to separate those out as well. But if you have this data in hand, then there are relatively few data points for you to populate to describe that. If you are only a cast house, if you are only doing casting, you would only enter the data under the cast house section, and you would have described a slightly different slope. You can see it's slightly lower here because you don't have the slab integrated into it, and your scope 1 and 2 slope would only be a cast house process slope. So if you're using only if you're a cast house only, you only populate that field. If you're semis only, the same, you would do it below, and again you would have a described slope accordingly. That's a whistle-stop tour, a lot to kind of get through, but we wanted to spend some time answering questions, and we have 10 minutes left, I think, to do that. So let me have a quick look and see if we have any questions that have come in on the Q&A.
Hello, everyone. Thank you, Chris. Thank you, Gangaa. Just to clarify for me, the GHG tools use only for alumina smile, or you can use for bauxite mine?
Yes, that's a great question. The underlying data that is produced by the International Aluminium Institute, it incorporates the bauxite and alumina emissions in that data set. The trouble is, it's very hard to split those out at the sectoral level. So for the ASI method, at the moment, the rules are that if you are a standalone bauxite mine, let's say in Guinea, I don't know, Sibége, or other bauxite mine in Guinea, or if you're standalone alumina producer, as in you're not integrated into an entity that has a smelter in system, you do not need, there is no requirement for you to have targets that use the ASI method. And actually at the moment, our method can't describe those slopes for standalone alumina or standalone bauxite. Part of the reason for that as well is that bauxite related emissions are very, very small in the aluminium sector, less than 1%. And so to describe the slope, you could see it's a very significant one for smelting. For mining, if you put it on the same y-axis, it would look flat and near zero. For alumina, there is some more. We are developing, and as part of the version 4 performance standard, we're hoping to release a bauxite and alumina version of the method. And if you get in touch with me, I have an informal version of one that does that. It's not published by us, but you're welcome to use that to describe some targets for yourself, but you don't need to. ASI does not expect you to. There is no requirement for you to do that. So at the moment, no, the tool can't be used for that in its published form. I do have a version available. So if anyone wants to get in touch with me, an informal version that does look at bauxite and alumina, I'm happy to share that. But for bauxite, I can tell you now that the emissions are so low at the sector level that really it looks quite flat out to mid-century. That's a great question and is often asked by others as well. Thank you.
They are basically in the die casting, and they have submitted, or you can declared on the SBTA regarding their net zero, and they have committed as well. Only thing is it for the die casting, whether they need to follow the same on this ASI, whatever the Excel sheet is there on the ASI website. So do they separately follow the same, or whatever they have already prepared the roadmap and support and submitted to the SBTI, is it sufficient for them?
It's a great question. As we develop version 4 of the performance standard, we're looking more and more to recognize science-based targets, especially for downstream industry, because increasingly they do SBT, absolute contraction approach. The upstream industry does not do SBT, and that's why we developed our own sectoral decarbonisation approach. What we ask, what the normative language asks for, is that targets have been set, intermediate targets, so that's 5-year targets, quite short term, I would say. I think SBTI calls those short term targets. We need those to be set using, they need to be set in alignment with a recognized method, and the only recognized method is the ASI method. So what we would say is that we don't take science-based targets as a given for conformance, but if the entity can demonstrate to the auditor that the science-based targets is broadly aligned with the ASI method output, then that is enough for us. You don't need to describe a separate slope. So I'm going to give you an example of the die caster. Let's say they've set an absolute contraction emission approach using SBT. That's about 40, that's around, let's say 2025. That's about something like 20 to 30% by 2030. So significant, right? That's an absolute contraction. We ask for intensity. As long as the entity isn't decreasing its production, then we could say that the intensity is about the same as absolute. So a 20 to 30% intensity reduction 2030, that is broadly aligned with the ASI method. So what I would encourage entities to do is put your numbers in the ASI method, check that they are aligned with your broadly, with some uncertainty, with the science-based targets target, and show the auditor that. So that they are broadly aligned. That's conformance. But what we don't do is take SBTI as immediate conformance. Yeah. So there's a bit of work to be done with the auditor. In fact, I've got another question on conformance, which is about mandated to plot the actual performance over the pathway to demonstrate compliance. No. What you are expected, the normative language expects you to do, is to have an intermediate target that is aligned with that slope. So in the next 5 years, you need to publicly disclose your target, and that target needs to broadly be aligned with the slope. You don't need to publish the slope in totality. Some entities do that because they want to demonstrate a 2050 line. And it's relatively easy for them just to do the tool and to publish as is. So we find a split. Some entities like to do that, and that leads to conformance because they've disclosed the slope. For other entities, they want to show alignment with existing corporate targets, and they don't want to have to show 2050 because there's high uncertainty there, so they don't. Both of those are conformant, right? But what is important is that the intermediate target is broadly aligned with the slope as described.
I just have a question regarding the inclusion of scrap. So we are including our emissions of scrap in category 1, which is purchased material.
Yes.
And I wanted to know if we need to include it in category 4 as well, which is the shipping of that scrap.
Oh, yes, you do. Yeah.
Okay,
yeah.
so both.
Both, yes. Yes, you do. Often that's not that's an interesting question, because often what we find is that the shipping of the scrap in many cast houses, it doesn't come from very far, but actually that is increasing. So yes, you would need to include the category 4 in there. But I would be interested in whether it matters, right? So one of the things you want to do when you're looking with these numbers, there's a high uncertainty, especially with scope 3, up to 20% uncertainty. So when we describe these lines, they're not really lines, they're bands. And I'd encourage auditors as well, when they are looking at conformance, to not look to decimal places because there's such high uncertainty here that the precision that the tool shows is kind of a false precision. So when you're incorporating the scrap, and let's say you give it a burden of 0 because you're using a cutoff approach, but you add in the transport emissions, category 4, and then you add in some remelt that you're bringing from primary, my feeling is, unless you have 100% or very significant scrap input, that actually that category 4 number is going to get lost. It is going to be immaterial. So take that into account. I will say in theory, yes, that should be included. But in practice, play around with the data and see whether it makes any difference at all, and whether the output, given that it has an uncertainty of probably 10 to 20%, whether that matters. So in theory, yes, these things should be used, but in practice, please use a materiality lens when exploring these different numbers, because what we want to do is for entities to be focused on decarbonisation, not on chasing down the last bit of emissions data that is going to take you a lot of time and a lot of effort, actually for very little difference in the slopes as described. Yeah.
Exactly right. It's just a tedious process to just go to that detail.
The more I look at some of this stuff, especially for the primary side of things, one decimal place is about as far as you're going to get, which is why I do roll my eyes a bit with CBAM when it asks for 3 decimal places for semi-fabrication and casting process emissions, because that precision is not possible, just not possible.
All right.
So, and this is maybe a message again to any auditors or registered specialists online as well, is be careful with precision. There is high uncertainty in all of these numbers, but there's also a requirement for the industry to decarbonize very heavily, right? And so if we're looking at 30% reduction by 2030, that's significant. It's a big number drop. The uncertainty, be mindful of that, and don't penalize entities that are making good efforts in that slope because they've missed their target by 2%, because the uncertainty in the data is such that that 2% really doesn't exist. We should work on our guidance as well to be a bit clearer on that, that we should be using, category 4 emissions should be included for scrap, but only where material. Where they're not, you can ignore it. How many footprints and volumes can you add for the midstream? Only 1. No, you can add as many as you like. You can do this site level, you can do it for across the entity. The system will mass calculate all of this for you. So let's say we have an example where you have a load of different cast houses. You've got one that's a smelter cast house, kind of low, and another one that has 300,000 tons and is doing something mid-range. The system will integrate all of those into integrated slopes. Same with your procurement as well. The thing with the procurement is you have to do the maths, right? So on the gate to gate, the system will do your mass weighting for you. For the procurement, you're going to have to do the maths yourselves, including yields for scrap, which I don't really have time to get into today, but is explained in the ASI method. How can you see if your slope is aligned with ASI reductions targets? Well, in a given year, you look at what your intensity is, calculated the same as for your baseline year, and whether it's in line with that number or not. Now, there is a high uncertainty, especially with the scope 3's data. And so as long as an entity can demonstrate that it is broadly aligned with that slope, I would say that shows conformance. We do, of course, have an exemption process because those slopes, even with a given uncertainty, are very aggressive. And we know that most entities are unable to meet those, at least in the short to medium term. So non-conformance for performance is valid then for exemption. So if you're not able to meet your slope, the auditor can trigger an exemption process, as long as you can demonstrate that you've done something towards the emissions reduction and you're systemically unable to achieve that slope. So if you're using ingot and scrap in remelt, you have to production weight. So I'm going to take an example and talk it rather than do it on the screen. You've got 10 tons of prime ingot. You have 10 tons of scrap coming in. And let's say the prime is at 10 tons per ton, and you use a cut-off approach, so your scrap is coming in with 0. So you have 10 tons of emissions divided by 20, so your emissions intensity is actually 0.5. But it's not quite, because you have to build in a yield to the scrap. So with a yield of 0.9, you have to multiply that emissions factor by 0.9. That's detailed in the ASI method guidance. So even though you're measuring the input to the cast house, you have to take account of the fact that not all of the aluminium that you bring in scrap will form part of the output. So you have to back out the losses on the scrap side. We assume 100% conversion for the prime ingot when it comes in. Can you please clarify again what emissions needs to be included in the 100% electrolytic tab, scope 1, 2, and 3? In the 100% electrolytic tab, when you're calculating your emissions intensity in order to bring it in, my advice, rather than going through this in detail now, is to say you use the IAI carbon footprint guidance for primary aluminium to understand the scope of emissions. And you talk there about scope 1, 2, and 3. It might be different for different entities, because some, let's say you're self-generating electricity, that would be a scope 1. For others, that would be a scope 2. Or if you're producing your own alumina, that might be a scope 1, whereas it's someone else's scope 3. So use the IAI carbon footprint guidance. It's referenced in the ASI guidance, especially for the primary aluminium. Essentially, the scope of emissions to be included in your intensity number is that described by the International Aluminium Institute. Now, once you bring scrap into things, it complicates it a bit, but for the 100% electrolytic, they're the data to be used. One thing to note, it doesn't apply to so many of our members, but certainly some of the emerging ones or some of the ones in China, is that some entities around the world don't they ship liquid metals. So you're tapping aluminium from the pots, you're keeping it in holding furnaces, and then you're not actually casting it at all. In that situation, the holding furnaces essentially play the role of the cast house. So you still include all of those emissions, and what you'll find is that those entities will have a smaller intensity than those that are casting. That's fine. You essentially measure the emissions cradle to gate at the output of the holding furnaces, and you treat the liquid metal as if it's a cast metal, but it will have a lower emissions intensity than others. That's just a function of scope.
Our company is creating or producing rolling slabs from scrap metal only.
Yes.
So there are very few uses for primary metal, which is normally provided by customers, already knowing that their scrap will not allow for the final specification required.
For you, if you're using 0 prime and 100% recycled content, you're going to have some very interesting slopes. In fact, 1.5 alignment has already probably been achieved by you because of the dominance of the scope 3 category ones. So, but we can explore that. Happy to do that in real time. I think folks should have my email address. If not, it's available on the website, and I'm more than happy to do tailored training for those who want it.
Thank you very much, Chris. Much appreciated, because I think that some of the questions are probably quite different. We use natural gas plus pure oxygen, for example, for all the burners. And so we have quite an amount of scope 1 emissions, as we don't use much of electricity in comparison. Okay, thank you very much. I will contact you.
Yeah, that's going to be interesting. Anyway, yes, we'll do that. That's going to be fun. And in fact, I've come from my background is more in the primary industry. I have to say, it's been interesting for me to come in and to see some of the cast house intensities that are coming through the system, which are much higher than I would expect. Like, because I'm used to smelter cast houses with inputs of hot metal and relatively low intensities. For lots of remelt ones, especially using scrap, the intensities are kind of higher than the sectoral data leads us to believe. Anyway, we can explore that offline. I have one final question, which I'm going to go to. I know we're a minute over time, but this is an interesting one, an important one. Total production output volume should take in rejected output that returns to furnace. No. Internal scrap is not seen by this system. It is seen in the scope 1 and 2 data, because every time you run internal scrap through your cast house, you have to melt it, and so you're using more thermal energy. So the scope 1 and 2 slope will incorporate the emissions from that remelt, but they're not part of your procurement emissions, right? So you'll be seen in the fact that they're not an output, but externally sourced scrap that will be seen in the procurement number. So that's important. It's also documented in the ASI method documentation. Externally sourced scrap is what forms part of your procurement emissions. Internal scrap is essentially netted out, and the emissions are seen in your scope 1 and 2. So if you're running a whole heap of internal going through the system, your emissions are going to be higher. Yeah.
Good. Thank you very much, Chris. Thank you very much, all of you. Thank you. Bye.
Thank you all. Bye-bye.